Recording in progress. Ladies and gentlemen, if I could ask you just to all please stand as we acknowledge and welcome the Deputy Minister of Science, Technology and Innovation to our meeting. Thank you. Thank you very much. This is a celebration, so you're supposed to make a little bit of noise as well, but thank you for that. Right, so I'm going to hand over to the chair of the meeting to continue, and just to remind you that we are live streaming the first part of our program. So I'm going to hand over to the chair, Professor Victor Chivase, also the chairperson of the CERN Consortium.
Good morning, ladies and gentlemen, and welcome to NRF Ithemba Labs, the premier research infrastructure platform for accelerator-based sciences and technology on the African continent. As he introduced already, my name is Professor Victor Chivase, Managing Director of Ithemba Labs and Chairperson of CERN. A special word of welcome to the Deputy Minister of Science, Technology and Innovation, Ms. Nomalungelo Gina, together with other representatives from the Department of Science, Technology and Innovation, DDG Research, Development and Support, Mr. Imran Patel, Director Charles Mkonoto. A special word of thanks goes to the Chairperson of the NRF Board, Professor Musa Mushavela, who prepared a voice message as he's unable to be with us in person. The Deputy CEO of NRF, Dr. Angus Patterson, together with the other members of the corporate executive, Dr. Thandi Mugwebi, Mr. Kidirang Wakile, Director of Accelerators and Technology at CERN, Dr. Mike Lamont, Professor in Theoretical Physics at King's College, London, Professor John Ellis, Deputy Vice Chancellor for Research, Innovation and Internalization at Nelson Mandela University, Professor Azwindini Muronga, and all protocol observed. At this stage, before I finish my presentation, I'll call upon our safety manager to deal with the safety brief before I continue.
Good morning, ladies and gentlemen. Can I please have your attention? At the back of this auditorium, there are two emergency exits. Please locate the nearest emergency exit to your seating position. Upon hearing the evacuation alarm, please make your way in an orderly fashion via the emergency exit to the lawn, the parking area where the assembly points are. Gather there and await further instructions from the evacuation marshals. If you do feel unwell during the course of the day, please make it known to any Ithemba Lab staff member or at the receptionist. We do have a first aid clinic on site, an occupational health clinic that is fully equipped, and we will be able to tend to your needs. For those of you who will be going on a tour of the facility, please pay special attention to all the signposting and warning labels attached to equipment or to the various controlled areas. For those who will be accessing vaults, please bear in mind that there are height restrictions as you access the area, and there are various overhead hazards. For those who will be accessing cyclotron vaults or accelerator vaults, please bear in mind that there are strong magnetic fields, so We prohibit access to those wearing or having implants such as pacemakers, and also access is restricted to any pregnant individuals or those under the age of 18, although I don't think that will be a problem today. Then pay attention to any radiation warning signs and only access vaults when escorted by a radiation protection officer, and the area status lights show green and access is permitted. Then lastly, all radiation areas that will be accessed will have an ambient dose rate less than 10 microsieverts per hour, and contamination levels will be negligible. Nevertheless, your occupational exposure will be monitored throughout the visit, and if you require the values, please make it known to the radiation protection officer, who will then provide you with the relevant certificate. Thank you.
Yes, what a joyous occasion to have you join us as we reflect on 15 years of the CERN consortium, where we use hindsight and insight to shape our collective future. I joined NRF Itemba Labs in June 2023, and what an amazing ride it has been. I was part of the inauguration of the SAFE, which showcases our expertise and competencies through the production of radioisotopes, which have and continue to make a great impact in the improvement of healthcare delivery, both locally and globally. And today we celebrate the advances made within the context of the high energy physics, content, skills, and training, collaboration, and technology transfer. Thank you for accepting our invitation to celebrate this milestone, but also to contribute to the conversations that will shape our future. Welcome to the celebration. I thank you. Without wasting time, I will call upon Dr. Mike Lamont to give us opening remarks.
Thank you very much, Deputy Minister, ladies, gentlemen, friends and colleagues. A real privilege and really very happy to be here on the occasion of the 50 years of CERN collaboration. And we can call this a journey of shared success. Now, I've got 20 minutes for opening remarks, and I started by writing down a text, which I was essentially going to read. So I thought, at the advice of Emmanuel, I threw a few slides together to take us through this journey. And so our goal is fairly straightforward: to understand the most fundamental particles and laws of the universe. Okay, now, as you imagine, this throws up a few challenges. And at CERN, just to guide us through this talk, going through the 4 pillars that underpin this mission. So research clearly, the technology and innovation that underpin it all, collaboration, an incredibly strong collaborative ecosystem, I'll come to this later, and education and training. So collaboration. So CERN was set up as a laboratory for peace, founded in the aftermath of the Second World War in 1954, with 12 European member states. We're now up to 24. Estonia joined last year to make it up from 23. 10 associate member states, 4 observers, and a wide-ranging global network of collaboration agreements, around 50 of those. And just to set the scene at CERN, our CERN employees, we have around 2,600 staff, around 1,000 graduates, and you see the number of associates, mostly users who come to use the facilities. And it really is a laboratory for people around the world. We're there to serve the experimental community, and you see that the CERN users come from a global pool. It's a diverse and cultural diverse collection of 110 nationalities. You see the number of users in brackets there coming from the member states, the associate member states, and these international cooperation agreements that span the world. And just we welcomed Brazil as an associate member last year. Just to show that the actual membership of associate member states is enlarging. India and Pakistan already associate members, and we have global reach here. There's experimental community in Brazil, of course, but there's also, they have a strong accelerator community driven out. There's a lab, CNPEM, just outside Sao Paulo, which has got a serious synchron light source, and we have strong links with their accelerator community there, which also fed into this process. So the power of collaboration, coming to the, we have a shared vision here for advancing society for humanity. There is combined strength, so we're able to, by working together, to be able to tackle these big challenges together, and of course assure mutual growth, building capacity, knowledge and opportunity. And I just flash a slide on the right there from Herwig Schopper, who's just recently passed 100 years, a former Director General of CERN. And this was a presentation he gave on the setting up of a synchrotron light source called Sesame in Jordan. And this includes countries like Egypt, Iran, Israel, Palestine, Jordan itself, and really an example of how in that sort of environment you can still use science as a vector for cooperation. And this from Eliezer, who was president of CERN Council until the end of last year. He finished his 3-year mandate. We are trying to build with the use of science understanding in the region. So they're talking about Sesame. The project is very special. Each of us brings its own history, its own wounds, its own scars. Each of us has our own interests, yet we have a common vision, which is to benefit the people of the region and the whole of humanity. And he tells tales over coffee about how they've managed to do it. You can imagine the meetings and some of the tensions that build up in the region, but nonetheless they've managed to hold true to this vision and keep this as a viable going concern today. I'll just flash this. I won't read through the words, but the high-level benefits of collaboration between South Africa and CERN, scientific advancement, being part of a global community, capacity building, inspiring the next generation of scientists and engineers, technological innovation, and cultural exchange, fostering respect, understanding, and collaboration across diverse perspectives. And we see this at CERN day in out in an incredible way. Just coming to research, I'm going to take this opportunity to bring you a brief up-to-date about what's going on at CERN. I mean, this is our core business, of course. We have our good days. So this is July the 4th, 2012. This is Fabiola, who was then Atlas spokesperson, announcing the discovery in Atlas of the Higgs boson. They passed the 5 sigma mark. And of course, this leading to the ultimate prize, free t-shirts. Just a brief, so at CERN, exploitation of our complex, our accelerator complex. In the medium term, the high luminosity LHC, this is going to take us out into the early 40s, so securing the medium term future. We're also looking at future options. Top of the list is the FCC. It's not the only one. The linear colliders, muon colliders in the mix there, but this is the preferred option for the moment. Not approved yet, quite expensive, and work in progress there. And all the technology and engineering and R&D that underpin this. This is hard stuff in the experiments and on the accelerators. And of course, we're pushing the limits of what's available to deliver what we do. This is the accelerator complex. I'll just run you through this very briefly. LINAC 4 takes H minus into the booster. We strip the electrons off on the way in and to produce the protons, which then go off to the rest of the complex. So we have radioactive ion beams at the Isolde facility. So a sister organization of the labs here, of course. Just to note that Medicis is a opportunistic facility. We irradiate targets, take them away from the complex and do mass separation to produce radioactive isotopes for medical research. Neutrons at the Neutron Time of Flight facility, antiprotons at AD Eleanor, primary protons and ions, secondary beams to the east area and the north area. Just to say that these are big communities. So between the eastern area, north area, there's 2,000 physicists on the books coming for a wide variety of experiments. At Isolde, a passionate community of nuclear physicists of around 1,000. So really, besides the LHC, a very diverse program. And we also do electrons at CERN's linear accelerator for research. And these are some pictures of the antiprotons, radioactive ion beams at Isolde, Atlas, of course, and CLEAR. Flagship, the LHC. So I say you go down there. I still go down there, and you wonder how it's ever going to work, but it does. And last year was a very good year. Impressive amount of integrated luminosity delivered to the experiments. All targets and goals were reached and often surpassed. Amazing performance and incredible achievements. John will come back to what we do with all the data, but this was the money plot from last year, and you see the integrated luminosity delivered in 2024 compared to previous years. So really, really very good. 125 inverse femtobars to Atlas and CMS. And just to remind you, a femtobarn is 10 to the minus 39 centimeters squared. So a ridiculously small area. And we offered the experiments last year 125 potential collisions in that area, which if you multiply up, gives them 10 quadrillion, what we call messy, inelastic proton-proton collisions. And in there, per experiment, 7.5 million Higgs-ish, of which they see about 10%. And we also finished the year off with ions. So again, a very good run, and you see events from the 4 experiments, Atlas and CMS, Atlas and LHCb. And this is modern day alchemy. This allows us to transform, by a rather elaborate process, lead-208, isotopically pure, into champagne. I won't, and you see I showed this before, but you see the bottles are getting bigger. And this is a present from Atlas, so this is a Methuselah, and big thanks to them. I won't go into the cost per bottle, but it's... And I just want one highlight from last year at CERN Medicis. This is radioisotopes for medical research, and one particular one of interest is samarium-153, which is an emitter which emits gammas and betas, and excellent theranostics. So you can do therapy with it and at the same time diagnostics. And in fact, this is produced in SCK in Belgium, a reactor, imported to CERN. Then we do mass separation. So it comes in with low specific activity, goes through mass separation, becomes high specific activity, and then can be used in a radiopharmaceutical. We do sample characterization, and the idea is to go to Heidelberg Hospital for actual clinical trials. So we've never actually done this. We've done preclinical trials with animal models as approved by our present regulations, and we went to council at the end of last year to seek approvals to use this for clinical trials, which would be a first for CERN. Technical innovation, very, very, very briefly. CERN, our prime drive, of course, is discovery and the creation of knowledge, but it costs a lot of money, and we need to, of course, justify our existence in a wider context. And CERN is seen by the European Union, for instance, as a research infrastructure. So a driver of innovation, integration of research communities, strong links to industry, collaborative ecosystem, societal impact, and outreach and education. So really taking its place in a kind of industrial context within society. On knowledge transfer, I just quote Fabiola: places like CERN contribute to the kind of knowledge that not only enriches humanity, but also provides the wellspring of ideas that become the technology of the future. And this I showed, it's a bit wordy, but we're discussing over dinner last night. This is clearly important, that the benefits from engaging in this basic research are clear. The UK commissioned a document in 2020, and just a few quotes from that evidence document. More details at the links there if you want to visit. But CERN supports state-of-the-art research. UK scientists build on this enhanced understanding in their research, supporting UK scientific achievement. Pooled resources, investment enables UK access, supports strength of UK research. And CERN's development and scientific goals drive technological advances in facilities and infrastructure. New innovations emerge, wider applications bring societal benefits. So really, this is part of what we should be delivering as a community for those that support us. And very briefly on education training, this will be addressed in a dedicated talk later in this meeting. But engaging in this, it opens a world of career opportunities. So you see the age distribution of scientists working at CERN. We have a big youthful cohort who come in. This is our talent pipeline. Some stay, but many go off to industry, to other fields, into academia and research. And just to finish off, CERN's training and education outreach program. Again, I won't read through this, but it's something we take very seriously. And of course, by either through the international collaboration agreements or associate membership, you have access to these programs. So my closing remarks. So I try to convince you that science benefits from international collaborations in numerous ways. It is a driver of excellence, diverse perspectives and expertise, combined resources to meet global challenges, economic and strategic benefits, and cultural cross-links. And there's no doubt about it, we are stronger together. Any one of us could not do this alone. It's part of a process, a thread in the fabric of human development. It's not the only one, of course. There's art, there's culture, there's sport. But working together politically, intellectually, culturally, scientifically, in the spirit of innovation, modernism, and cosmopolitanism takes us forward. And we make progress on the back of the Enlightenment values of reason, science, and humanism, with technology and wealth generation playing their part. And if you look back, Steven Pinker wrote a book on enlightenment called Enlightenment Now, and just charting how far we've actually come, but it is a struggle. It's clear there's forces today that we don't have to look, we see the new president of the US taking over. This is something we really have to work with as a community to carry on pushing this forward. So I'll finish there with just expressing our profound gratitude to South Africa for its support and commitment. And we look forward with confidence to our partnership's future and the next 15 years. Thank you very much.
I wanted to summarize, but I think it would be very difficult. The only sentence that I would mention is we are stronger together. From here, we are going to listen to a pre-recorded message from the chairperson of the board of NRF, Professor Musa Mshavela.
The National Research Foundation is celebrating 25 years of research, impact, partnerships and innovation in 2024-25 year cycle. This creates an opportunity for us to reflect on what has been achieved through our commitment to advance knowledge, inspire our nation and transform lives. The CERN program was officially launched on the 15th of December in 2008, and then it was chaired by the late Professor Jean Clements, based at the University of Cape Town. There was an article published then in the Cape Argus in 2002 with the heading, "City Boffins Join Alice for a Big Bang," which could be seen as South Africa's introduction to big collaborative science. South Africa has a rich and proud history of experimental science that dates back to the 1950s with the establishment of the National Center for Nuclear Research and Training in Pretoria. It is my view that the pursuit of fundamental particle physics can become a driver for innovation and societal benefit if we not only focus on content knowledge, but also include skills development. The skills are associated with the new and emerging technologies that are embedded in big science projects. These projects range from physics data analysis that employ cutting-edge statistical, machine learning, and data analysis techniques, to hardware-oriented activities including major contributions to new detector upgrades, maintenance, and operation. The CERN environment has been an unparalleled training and development hub over the past 15 years that offers unique possibilities to South African scientists and students through immersion within its world-class context. I'm aware that even our local industry has benefited from the partnership with CERN as South African collaborators are granted opportunities for in-kind contributions to CERN detector upgrades. The intentional focus of the CERN program on the integration of historically disadvantaged institutions in recent years has initiated conversations related to the transformation and the importance of context in lived realities. I am delighted to hear of the enhanced participation from the HDIs, as we call them, that was facilitated by the development of research infrastructure at local universities. This includes the high-throughput electronics laboratory at the University of Zululand. The success of the CERN program calls for the enhancement of its ability to provide broad economic impact to South Africa. The maturation of the program implies an increase in the capacity of local universities to train the specialists needed to perform and facilitate the transfer of technology to the country. This transfer will become the driver of innovation and thereby magnify the positive impact that science has in improving the quality of life of all South Africans. So, there is more work to be done, we know this, and congratulations on achieving this milestone. What an amazing opportunity for South Africans to celebrate the participation and growth in high-energy experimental and theoretical physics through this event. We are looking forward to see and experience the impact of the program in the coming years. Thank you very much and best wishes.
You can see we have done that again. As physicists, we always move with the speed of light. I wanted to also to shake hands. I like to shake hands when people are done speaking, but unfortunately it could not be. I could not do that here. The next speaker will be giving us reflections of the 15 years of the LHC physics, and it will be done by Professor John Ellis from King's College, London, and CERN. Thank you. The stage is yours.
Okay, so I'd like to thank the Deputy Minister and all my colleagues here in South Africa for this invitation. For me, it's a very meaningful occasion. I should say that the first time I came to South Africa was in 1985. And at that time, nobody knew what was going to happen, and a lot of people were very pessimistic. But I think that this room shows that that pessimism was unjustified, and I congratulate South Africa on the progress that it's made since my first visit. I would also congratulate South African physicists on the progress that you've made in the 15 years since the official South Africa-CERN collaboration started. I have a shoulder bag from a previous South Africa-CERN meeting, and it was a very good meeting, but it was a much smaller meeting than this one. And it is fantastic to see a room full of South African physicists sharing together the successes of the past 15 years, and we hope also the successes of the future. So, after a brief introduction to where we are with particle physics, I'll focus down on the Higgs boson, which was mentioned very briefly by Mike Lamont. The discovery of the Higgs boson in 2012 was undoubtedly one of the highlights, if not the highlight, of LHC physics over the last 15 years. So I'll discuss a bit the run-up to that, and I will also discuss the puzzles that we're now faced with. The Higgs boson is an extremely mysterious particle, different from any other particle. And one of our tasks at the moment, I speak as a theorist, most of you are experimentalists, is to try to unravel the mysteries of this peculiar particle. So there are various ways in which we try to look for physics beyond the standard model, beyond the Higgs model at the LHC, and I'll discuss some of those. A particularly interesting topic, if I may say, at the moment, is that of top quark physics. And I'll talk a little bit at the end about puzzles that have recently arisen in top quark physics, which may indicate an interesting discovery for the near future. So I don't know whether people still remember this terrible person. So he's famous for talking about known knowns, by which I include the standard model of particle physics, which describes, for a large part, the visible matter in the universe. He also talked about known unknowns. things that we know must be there, but we don't know what they are. And one example of that is dark matter, which makes up most of the matter in the universe. He also talked about unknown unknowns. What are they? Well, of course, by definition, we don't know what they are. Those are the things that we set out to explore when the LHC started operation 15 years ago. I've added a fourth line there, which is an unknown known. So what do I mean by that? Something which actually theoretically was known should exist, but I think not very much attention was paid to it. And as I'll discuss at the end of my talk, it now seems to be emerging from LHC data. So on this slide, you find summarized the content of the universe, the fundamental particles that we talk about, that we explore, that we study, and to some extent understand within the framework of what we call the Standard Model. The Standard Model is not a very fancy title, but in fact, this is an extremely powerful mathematical theory which has been verified in many experiments with very high precision. So in the top half of the slide are listed the fundamental constituents of matter, the quarks that make up nuclei, that make up cores of atoms, the electron, which orbits around the nuclei, and related particles. And in the bottom half of the slide, you have the fundamental interactions between the different types of particles. Two of them are very familiar: gravity, electromagnetism. And then on the lower right-hand side, you have additional forces which act inside atoms, inside nuclei, the weak force that causes forms of radioactivity, and the strong force that holds nuclei together. And the major achievement of the Standard Model is to provide calculable theories of those interactions. Now, of course, I cheated you a little bit, because there was one element on that previous slide which was missing. That previous slide talked about particles, but it didn't say anything about their masses. And fundamental particles do have masses. If the electron didn't have a mass, it would run away from nuclei at the speed of light, and there would be no atoms. So Newton, of course, said mass is related to weight. Einstein said energy is related to mass, E equals mc squared. But neither of them explained where those masses come from. And this gentleman that you see here is Mr. Higgs, who came up with a theory, which is on the blackboard behind him. And according to his theory, there had to be, in addition to the particles on the previous slide, an additional particle, the Higgs boson. So he postulated that particle in 1964, and it became, in some sense, the holy grail of particle physics to find that particle, and it was discovered at CERN in 2012. So on the slide, I've just summarized a few of the key dates in the LHC, and my colleagues will correct me if I got it a bit wrong or missed something out. So the LHC was actually approved by the CERN Council in 1994. It started up in 2008. There was a technical problem. The first collisions didn't take place until 2009, and the first high-energy collisions took place in 2010. So for me, that initiates the 15 years of LHC physics that we're talking about. The first hints of the Higgs boson came in 2011, the discovery in 2012, Nobel Prize for Peter Higgs and his colleague François Englert in 2013, and since then, exploration of the Higgs has continued. Searches for other new particles are ongoing at ever higher energies and, as Mike Lamont has described, with ever increasing numbers of collisions. Now, a couple of slides back, I just sort of listed the fundamental particles, and I said, well, we have a standard model that describes them. So this is a mathematical structure which is quite complicated. Well, to many people it looks complicated. I'm a theorist. To me it looks simple. But at the bottom there you have the fundamental equation which describes the interactions of the particles. The top two lines are pieces of the puzzle that were tested very thoroughly by experiments before the LHC got started. The bottom two lines, you see a symbol called phi. Phi represents the Higgs, and those two lines were completely unknown before the LHC started. And what the LHC has been doing is verifying those two lines of the theory, very important aspect of the theory, and testing it with ever higher precision. So I've been talking about the discovery of the Higgs boson, which came in 2012. So the discovery was made by two of the large experiments at CERN. And here is an event which was observed by the ATLAS experiment. So what you see there are four almost straight red lines emerging from a collision. Those four red lines are, we think, the tracks of muon particles which were produced by the decay of a Higgs boson. So just on the basis of one event, you can't claim that you've discovered a new particle. You have to see a statistically significant excess. And on July the 4th, 2012, the ATLAS collaboration, together with its partner, the CMS collaboration, announced that they had observed such statistical excesses, clear evidence for the existence of a new particle thought to be the Higgs boson. So, of course, I should remind you that one of the pillars of SA CERN is its participation in the ATLAS experiment. So many South African physicists participated in this discovery. So there's a couple of people on this slide whom you've already met. The guy on the right, that's Peter Higgs, who predicted the existence of this particle. The lady bottom left is Fabiola Gianotti, who announced the discovery of a new particle by the ATLAS experiment. And of course, she's gone on to become the Director General of CERN. And in the middle, you have Francois Englert, who also proposed a theory similar to Peter Higgs. But he somehow omitted to predict the existence of a boson. So that's why we call it the Higgs boson, and not the Higgs-Englert boson. Anyway, behind them you can see all sorts of happy faces the day of the discovery of the new particle. So Mike has already shown you a version of this slide, but I think it's worth repeating. So this discovery of the Higgs boson was not made by CERN. It was made at CERN by teams of literally thousands of physicists from countries, dozens of countries around the world, over 100 nationalities, as you've heard, and in particular, scientists from South Africa. So South Africa now has dozens of scientists registered as working on CERN experiments. We have an international cooperation agreement between South Africa and CERN. And as Mike mentioned, CERN would be very open to increasing this collaboration if South Africa finds that that would be interesting. Okay, so back to July the 4th, 2012. So a new particle was discovered, but was this really the Higgs boson that we were looking for? Or was it some sort of an imposter? So it's necessary to check that this new particle behaved in all the ways that we expected. In particular, that meant that this new particle should couple to other particles in very specific ways, very different from any other particle. Specifically, the couplings should be proportional to the other particles' masses. So that was a key prediction. So the LHC experiments set out to produce lots of particles, in particular lots of Higgs particles, and check whether the couplings of those particles, and in particular the couplings of the Higgs particle, were what was predicted within the standard model. So this is just a very simple little summary, but it shows you that many, many measurements have been made at the LHC, and that generally they all agree very well with the predictions of the standard model. In particular, they enabled the ATLAS and CMS experiments to check whether the Higgs particle coupled to other particles the way that was predicted. Specifically, the couplings would be proportional to their mass. That's what you expect. If the Higgs particle is responsible for particle masses, its couplings should be proportional to those masses. And as you can see here, on the horizontal axis, we have plotted particle masses. On the vertical axis, the couplings of this new particle, and all those couplings are consistent with being proportional to the other particle's mass. And this is unique. Other particles don't look like this. The photon, for example, couples to electric charges. Electron has charge -1, the proton has charge +1, but there's a simple numerical relationship between them. But you see the couplings of the Higgs boson vary over many orders of magnitude. We have absolutely no idea why. It's just the way things are, but we have to try to understand why things are that way. So I just wanted to take a couple of minutes to discuss a couple of ongoing measurements of the Higgs boson, which go beyond what I had on that previous slide. One is the decay of the Higgs boson into a photon and a Z boson. Z is the second heaviest bosonic particle. This is the first decay of the Higgs particle which does not go to a pair of particles, like two photons or a pair of bottom quarks. So this is an unequal couple of particles. And, well, it seems to be there, roughly speaking, in agreement with theoretical predictions, maybe a little bit higher than what is predicted theoretically. And so one of the ongoing topics is to measure that more precisely and to understand whether there's possibly some discrepancy with the prediction of the standard model. In the standard model, in addition to the Higgs coupling simply to other particles, there are also couplings where the Higgs boson couples to itself. And there's a couple of interesting couplings of that type which are now being explored. One is between 3 Higgs bosons, and one is of 2 Higgs bosons to 2 massive vector particles. So these are very firm predictions of the standard model. They have to be there, otherwise the whole structure of the theory would collapse. But there could be extensions of the standard model in which there will be deviations from the predictions. And I would say that measuring them is the next or the opening frontier in Higgs physics. So I won't go through this picture here. It's a whole bunch of diagrams which describe the way in which these nonlinear Higgs couplings contribute to the production, for example, of pairs of Higgs bosons, or the way in which they modify the measurements of single Higgs bosons. And both ATLAS and CMS have embarked on measurements of these couplings. They're often phrased as a search for the triple Higgs coupling. And that's indeed very important. So down the bottom right, you see where the measurements currently are. We cannot say yet whether that triple Higgs coupling is there, but it cannot be much larger than what is predicted in the standard model. The point which I find interesting is that we say this is one of the unknown knowns. So in the standard model, there has to be a coupling of two Higgs bosons to two vector bosons. And people haven't thought about that very much. But it turns out that those ATLAS and CMS measurements tell us that that coupling has to be there at a very high level of significance. And this is the first time we've observed a nonlinear Higgs coupling. So at this point, if you are running a funding agency, you might say, well, it's great that you've been able to verify all the predictions of the standard model. So that means you've finished with particle physics, nothing more to do? Well, actually, no. I would argue that by verifying the predictions of the standard model, we've got a firm basis for exploring what lies beyond, in particular, for example, the search for dark matter. And I've got a quotation here which expresses that thought. It's a poem by T.S. Eliot. To make an end is to make a beginning. The end is where we start from. And so the LHC, I think, is now in a phase very much of going on a journey beyond the standard model. And in this, I am aligned with James Bond. I don't know if you remember this movie, The World Is Not Enough. Well, I paraphrase that. The standard model is not enough. There must be physics beyond the standard model. And I'll give you a few reasons for that. I already mentioned the existence of dark matter. The standard model doesn't explain the origin of the matter in the universe. I've already mentioned it doesn't explain why particles have the masses that they do. Many other things. In particular, the Higgs is threatening to end the universe. If you do a careful calculation in the standard model, you find that empty space is unstable. And you predict that the universe will eventually collapse. I don't believe that. I believe that means that there must be additional physics beyond the standard model waiting for us to discover. So I would say that everything about the Higgs is puzzling. There's a pattern of couplings to fundamental matter particles, what we call Yukawa couplings. We don't understand them. There's a question of the absolute size of the mass of the Higgs boson. Don't understand that either. There should be a fourth order coupling of the Higgs boson. It has to be there in order that the electroweak theory work in the way that it does. But as I already mentioned, careful calculations indicate that that theory is intrinsically unstable. So everything about the Higgs boson is a puzzle, lots of things for you students to sort out. that the older generation failed to do. Let me just say a little bit about the magnitude of the Higgs mass. So you can write down a theory with whatever value of the Higgs mass you want. Fine. But then when you do quantum calculations, you find that they are divergent. If your calculation is divergent, that sounds like bad news. But you can calculate the divergence, you can cancel out the divergence by pairing up bosons and fermions. And that is what happens in a theory called supersymmetry. So supersymmetry, often called SUSY, is a theory that I fell in love with about 45 years ago. So far, there's no experimental evidence for SUSY, but I still love her. In fact, I would even argue that there's been additional indirect evidence in favor of SUSY for measurements at the LHC. It would sort out this problem of the instability of empty space. It made a successful prediction for the mass of the Higgs boson, predicted that couplings of the Higgs boson should be similar to those in the Standard Model. And there's all sorts of other things that it does, like, for example, it could provide dark matter. So maybe I should say a little bit about this instability problem. So the horizontal axis here represents the value of the Higgs. And that little red dot on the left-hand side represents where we are. So the Higgs has a value in empty space, and that then gives masses to all the fundamental particles. The trouble is that if you extrapolate to high fields values, you find a lower energy state over there on the right-hand side. Quantum mechanics tells you that the universe is doomed to go down into that lower energy state in what we call a big crunch. You would have to postulate new physics to stop that happening, and my favorite, SUSY, would do that job very well. So I won't go through the details of this calculation of the instability of the universe, but it depends on the precise values of the mass of the Higgs boson, which has been measured, and the mass of the top quark, which has also been measured, but perhaps not quite so accurately. And so an ongoing task for ATLAS and CMS is to improve, in particular, the measurements of the top quark mass, so that we can really firm up this observation that the universe looks like it might collapse. So I already mentioned that people have been looking for supersymmetry, and they haven't found it. I should mention they've been looking for a lot of other possible extensions of the Standard Model, haven't found them either. And there's a lot of sort of heart searching now in ATLAS and CMS, how they continue those searches, whether they should do searches in a different way. But I would express a little bit of caution, because when experiments say, well, we haven't found supersymmetry doesn't exist, just a second. Many of those searches have holes in them, and you should not necessarily take them at face value in the most general form of supersymmetric theory. So I think that there's a lot of scope for refining the searches for supersymmetry and other types of new physics, in particular with the much increased luminosities which are now coming from the LHC. So to quote the knight in Monty Python, supersymmetry is not dead yet. So one of the ways in which you can look for physics beyond the Standard Model is to look for its indirect effects. And here I have another quotation for you, not an Anglo-Saxon poet, but a Chinese military strategist who wrote, "The direct method may be used, look for new particles. But indirect methods, look for their indirect effects, will be needed in order to secure victory. The direct and the indirect lead on to each other in turn. It's like moving in a circle." Obviously, he foresaw FCC. Who can exhaust the possibilities of their combination? So this idea of looking for the indirect effects of heavy particles goes back many decades. Back in the 1930s, Fermi postulated a theory of the weak interactions which involved 4 fermions meeting at a single point. But nobody believed that. They believed that interaction was generated by the exchanges of massive particles. In the 1950s, it was established that the interaction had the form of 2 spin-1 objects. And so people said, well, that intermediate particle must be a massive vector boson. And then Peter Higgs went away and wrote down a theory where you could give mass to a vector boson, and the rest, as they say, is history. So there's a whole research program taking place now where we look at the interactions of the fundamental particles. And we ask whether there may be, in addition to the expected interactions in the standard model, additional interactions. Interactions like that 4 Fermi theory of the 1930s. And this is, I wouldn't hear, it's a model-independent way to look for physics beyond the standard model. It's perhaps overstating, but at least it's an agnostic way to look for new physics beyond the standard model. This can get a little bit complicated. So here I've simplified it, so it only looks rather complicated. Anyway, cutting to the chase, we've been involved in looking to see whether any of those possible new interactions might actually be present. And I have to say that so far we haven't found any indications. There's no significant deviation from the standard model. And that suggests that whatever new physics may be out there may be new particles weighing at least 1,000 GeV, a TeV, which, to my mind, motivates more luminosity, Mike, and motivates FCC to look both directly and indirectly for such new particles. So the last topic that I want to discuss is the top quark. So the top quark is the heaviest known particle. It weighs more or less the same as a lead nucleus, but it behaves like an elementary particle. And the LHC, with the number of collisions and the center of mass energy, is now able to produce many top quarks in various different ways, single top quarks, pairs of top quarks, even 4 top quarks have been observed. And again, you see in this picture here that these many different final states generally agree with the standard model prediction. But there's been a little nagging puzzle over a few years now. If you go back to a pair of a top and anti-top particle very close to the production threshold, there's been a couple of hints that maybe there were more pairs being produced than were expected. And that's shown by the little red data point upper left in the left plot and the black one on the right plot. So many people said, bullshit, this is a statistical fluctuation. Or they said, bullshit, it's just that we haven't been able to do the standard model calculation properly. Or, no, it's bullshit, add in some additional interactions and the effect will go away. But it hasn't. Now, there's another interesting picture of what happens when you're very close to the top anti-top threshold. So the top quark has spin, like the electron has a spin. And when you produce it at threshold, the spins of the top quark and the anti-quark could be correlated. And the way in which they are correlated depends on the way in which they are produced. Are they produced through a scalar channel, no spin, no net spin, or through a pseudoscalar channel, no net spin, but negative parity, or are they produced in some other way? And so there's been a lot of interest experimentally in measuring the correlation between top and anti-top spins to see how those things were produced. And the Atlas collaboration in particular has been looking at this, and the left plot shows that there is indeed significant correlation, I guess I should call it anti-correlation, between the top spin and anti-spin close to threshold. So just recently, the CMS collaboration has published an analysis which indicates that actually there really is a significant excess of top anti-top at threshold in a very particular spin state, so-called pseudoscalar state, spin zero with negative parity. And this is the sort of money plot from their analysis. So what could this be? Sorry, this is just a plot saying that in order to find this excess, they had to look at a very specific spin correlation that I won't go into in detail. So that was CMS. So Atlas is looking to see whether they find a similar effect. And so far, they have not been able to confirm it. So maybe this really is bullshit. But maybe not. And I at least am asking myself whether CMS is actually discovering a new boson, which would have a mass around 340, 350 GeV. And if it is discovering a new boson, is that a new fundamental boson, a new Higgs boson, which would be truly exciting? Or is it a bound state of top quark and anti-top quark, a thing called toponium? So this is actually something which for a long time has been predicted to exist. So theorists knew that this thing should be there, but I think that nobody was expecting it to be detectable at the LHC. And in particular, I think experimentalists were not really focusing on looking for toponium at the LHC. So that's why I call this an example of an unknown known. It was known, but not very widely within the community. So, as I said, there are two possibilities for this enhancement that has been seen by the CMS collaboration. It's either an additional fundamental boson, or it could be a top anti-top bound state as predicted in QCD. And on the right-hand side there, I've illustrated the diagram which generates this bound state, which I would emphasize again is theoretically well understood, but maybe not very widely known. And here I show again calculations which indicate on the left-hand side, theoretically, the bump that you would get from this bound state, and on the right-hand side, how that might show up in ATLAS or CMS. Now, I come to this from the point of view of somebody who's looking for physics beyond the standard model and would love this new object to be a new fundamental boson. And so when I heard about this CMS observation, together with a couple of my colleagues, we dug out some old calculations that we had done as to what such a particle would look like. And we dusted off our calculations, and this is what you see here. What's interesting is that this particle, if it's there, would interfere with the standard QCD background and give you a very interesting structure. So both the fundamental boson and the toponium models agree perfectly with what's been observed. Wait and see. Will ATLAS confirm CMS? Can one think of some way of distinguishing between the new boson and the toponium hypotheses? Okay, so that really brings me to the end of what I wanted to say, but I should confess that I've been very unfair to the other big experiments at the LHC. I've been unfair to LHCb in particular, which has been looking at CP violation, matter-antimatter symmetry, and has made many exciting measurements, in particular discovering CP violation in the charm quark system. And I've also completely neglected heavy ion collisions, but there I have an excuse, because Urs Wiedemann is going to give a talk tomorrow, and he's going to talk about heavy ion physics, of course. But here I just show a couple of slides, one on jet quenching and one on the viscosity measured in the fluid produced by heavy ion collisions, which I find particularly interesting. But I think Urs and also you, Mark, will come back to this in your talks. So my final slide. The standard model is wonderful, and it agrees very well with the visible matter in the universe. But, maybe it's going to be sunk by Higgs physics. Certainly, dark matter is waiting out there. And maybe there's a new boson waiting out there. Maybe there are unknown unknowns out there which will sink the standard model. Thank you.
I'm tempted to summarize again. Earlier I said, as physicists, we can move with the speed of light. And in the presentation of John Ellis, he said we cannot move with the speed of light because we have mass. But what we have learned is that we can use some words like bullshit. With those words, I'll call the next speaker. The 15 years, we continue again with the reflections of the 15 years of the CERN by calling Professor Azindi Muronga, who was the DVC research at Nelson Mandela University. The floor is yours.
Thank you very much, Program Director, Honorable Deputy Minister, distinguished guests, colleagues and friends, ladies and gentlemen. It is an honor to come and speak on behalf of a very successful consortium. It's a huge task. Thank you. It's a huge task to speak on behalf of the consortium, and I hope I will cover everyone else who is in the consortium. And the presentation is not mine only, it's contributed by consortium members as well. So thank you very much for inviting me again, Program Director. And I hope I will be able to use this fancy tool. I was not inducted how to use it. So I'm not an experimentalist, so I might mess up, but I will try. So this is where we start. We stand on the shoulders of giants. We stand on the shoulders of those who came before us. And we remember them because they are what I call Majakandira, which means trailblazers for our program. And those who have been with us along the journey, you will see that these two gentlemen who have departed have fought so hard, John Ellis, for this room to be filled today. We started small, but we are here and we also honor them. The consortium or the program that I'm going to speak about, you have already seen some of the slides. And we have 6 pillars of the consortium, the program itself. We have heard more about Atlas. And however, South African Atlas is involved in exploring fundamental particles and forces, including the Higgs boson that we just heard about. We also have South Africa ALICE, a group, which we will know more about the quark-gluon plasma probably this afternoon and tomorrow. And we also have ISOLDE, more on the nuclear physics lower end. We have heard from Mike Lamont about technology and innovation. And we have a new pillar, which was not there about 5 or 15 years ago. And that deals with technology transfer. And the reason it's there, it's probably obvious for us in South Africa, where we need technology transfer and innovation as well. We also have the theory division, which is very fundamental and core to understand what John Ellis was talking about there when he said, I simplified it. You will need the theorist to assist experimentalists to understand the physics at LHC. We will also speak about engagement. After all those slides that John Ellis put across, will our elementary school children be able to understand? In order for that, you need to engage the young and the old, of course, the public. So I will scan through these areas in the presentation. Because in South Africa, we have policymakers, and therefore they are interested in the programs that we have. How do these programs assist them to deliver on the mandate of their policies? We have what we call the National Developmental Plan 2030. How is the South African CERN program assisting to achieve the goals of the National Developmental Plan? We also have the 2019 Science and Technology and Innovation White Paper, which also give an avenue, and it enables programs like SA CERN to flourish through the support that is enshrined in the STI white paper. And therefore, in return, DSTI will want to find out when it go back to the public to say, look, SASN is here and they're assisting us in our challenges that we want to address in the National Developmental Plan. And then, of course, recently, the Decadal Plan on STI. And if you look within these policy documents, you will realize that South Africa's CERN program has a critical role to play to assist the government in realizing its goals. Just to pick up from the white paper, and there is this quote by one of our former president, Kgalema Motlanthe, who says, "No modern society has scaled the heights of social progress without science and technology." That's in the white paper, speaking to SASN program itself. Harnessing the force of science and technology to meet South Africa's developmental needs is amongst the surest way out of the current quagmire of underdevelopment. So there is an expectation that our science, our fundamental research, need to lead to the application in order to solve the country's program and problems. And in doing so, we understand that South Africa is not in an isolation. We are part of a continent, and therefore there is also an expectation of us playing a role on the continent. What will be South Africa's role in Agenda 2063, the Africa we want? In line with that, do we see South Africa's CERN addressing some of the UN SDGs? These are also coupled. And this is the presentation that I presented to African students in Marrakesh during the Africa School of Physics 2024, where we were showing that African students need to understand their role on the Africa Agenda 2063, as well as the UN SDGs. In terms of the high energy physics and the context of South Africa, it predates the 15 years. There has been those before us who contributed before the formation of the SASN. Mandelstam, John Dorfman, Werner Israel, Saul Tekluxi. You can list, including even the current existing colleagues here in South Africa, George Ellis, and as well as others who have contributed, and we will hear about them throughout the two-day proceedings. And of course, in terms of the science itself, the breakthroughs were already there. There have been papers published way back in the 1950s, 1960s, where colleagues and those what I call them Majakandira have been already contributing to international science. So we are not starting something from scratch. We are again standing on the shoulders of those who came before us. And the list, including the current ones, including the late John Clements, were the papers that were coming from South Africa before the formation of SASN, were making an impact. The paper on strangeness, we might hear more about it in heavy ion collisions. It's a well-cited paper. Of course, we know the contribution by John Clements on statistical hadronization and thermal physics in heavy ion collisions, and the string theory groups and many groups that were there before that led to the formation of the SASN consortium. Considering the current standing, which perhaps also led to the formation of the program, is the picture that we see here, that only 0.5% of CERN users are from Africa, and probably the majority coming from South Africa. But it's good that other African countries are joining forces. But we also have a challenge and an opportunity, and this is because of the bulging population of the African youth. which I will show in a moment. But the status of high energy physics in Africa will need interventions. And we are glad that in South Africa, our government is very supportive of this program. And I say this because we are comparing ourselves also with other regions like Latin America. They are starting to form their own programs, own consortia, so that together as developing countries, as we start talking about BRICS, as we start talking about South-South relations, we start to collaborate in these regional cooperations. So this is the rise of Africa's youth populations, which poses challenges but also opportunities. And challenges because we need to plan for the rising population of Africa's youth. But through Africa's CERN and SA CERN programs, we can start to address some of these challenges. You see this map, which is showing from 2 countries in Africa that were participating in SA CERN. The map of Africa is red, but it's also misleading because what is in the red is the students that come from South Africa and being trained in South Africa. And when you look at the nationalities spread across the continent. It's also a good thing because it means South Africa is playing its role on the continent by building capacity for the rest of the continent. We should encourage that, but we should also aim to see these programs spreading across the continent. That should also be our focus as a South Africa CERN program, to train them, but also to encourage them to go and form the similar programs in other African countries. And this has already slowly started. And we appreciate the work that is done by DSTI as well as NRF to make sure that there are strong collaborations on the continent. Of course, another opportunity is that training students within SA CERN, we don't only train them for high energy physics, we train them for all other disciplines, including astrophysics, where SKA should not be a white elephant. And therefore, we are contributing through our programs as well. We do have facilities here in South Africa where the SA CERN program could contribute and partner. We have the SKA Meerkat Salt Sarau. We also have the NIFEX CHPC, as well as South Africa's high education institutions, where SA CERN has collaborations and partners with those inbound entities. And as we have already heard, we have high energy and nuclear physics through SA CERN, collaborating with CERN, JINR, GSI, and with the discussions around the Africa Light sources, we hope that the continent will start to have its own large infrastructure as well. So it has been a journey for the program, starting already in 1992 with the signing of an MOU between the then FRD, now NRF, with CERN. And in 2005, we had a visit by the Department of Science and Technology, Mr. Mangena. We also had another visit by Minister Pando in 2011. And this shows that South Africa has been interested and supportive of its scientists when it comes to international collaborations and international engagements. And we also had Minister Mamoluko Kubai also visiting CERN, which shows commitment. They want to see where our scientists spend some of their time and most of their times, especially our students. And the consortium itself really, as John was saying, when he came for the first meeting, probably a small room only, full of people. And it's because it started with just a group, UCT joining ALICE in November 2001. Then there was a UCT CERN Research Center that was formed then, led by Jean Clemens and Zebulon Vilakazi. And this led, of course, eventually to the formation of CERN as a program in 2008, in 15 December. And the room was still not filled to the brim like today. But that was a signal of a program that was growing as well. Other universities joining ALICE as well. We had CHPC coming to assist us as well in terms of computing. And I think this was referenced by the chair of board of NRF, this article. Yeah? This is the article he was referring to in the pre-recorded speech. And we started small groups. And these are what I call the Majakandira of the program that you see today. Some of them are no longer there. Some of them you'll see them. They were in their own spaces. Some of them were working alone at that time, especially in theory. Some of them started forming groups. You will meet some of them and you can talk to them. And the picture on the bottom right, I think that was also during the launch on December 2008. You can see how small we were then. But along the way, we had small groups that culminate into today's full room. And as Pelelanga, we are not all here. Only few are here. The group has really indeed grown up. And this was some of the launch events, of which, again, John Ellis was there really supporting us as always. Peter Steinbeck, and some of the usual suspects who were there, wondering what the future of CERN might hold. But today we are here. It has indeed been a journey for us from UCT CERN to CERN as a national program. And the chair of NRF board emphasized that the program should be national by including historical disadvantaged universities. And those universities are now starting to be included slowly but surely. And that will reflect a true national program indeed. So the CERN program, as I've already explained, it started as a consortium of researchers who had some long-standing research programs with CERN. It was modeled along the Australian and Indian or Brazilian models. And there was an agreement that Itemba Labs will act as a neutral venue. This is the venue where we are in today, and Itemba Lab has done a sterling job to act as a neutral venue for the program. And the structure at the launch was as it is, with the chair sitting and with the 6 pillars that I've indicated. Then it was ALICE, Atlas, Isolde, and Theory, and now we have the technology transfer as well. So this is just a distribution of institutions that are participating in some of these pillars. In this case, for ALICE, we do have Itemba Labs, we've got University of Cape Town, and we have got VETS. And we do have principal investigators in each of these pillars. And I'm not listing the many postdocs and the many students underneath them. And they have been participating heavily at CERN, as you can see with ALICE matters. It means they're not just sitting here in South Africa, but really they're spending time at CERN. And thanks to the contribution by DSTI, this is possible for our students to go and participate at CERN. And then we have Atlas, probably the largest group in the consortium, with formerly UJ, VETS, Zululand, also Itemba Lab, and UCT. And indeed, in terms of tech transfer, which we will talk about, and Mike already spoken about, we are starting to see fruits in terms of the establishment of the electronics labs at the University of Zululand. And here is one of our consortium members trying to convince then Minister of DSTI that if you invest, we are coming back home to innovate. And indeed, that's what's happening today. And the students are the ones that are actually leading in developing some of the R&D equipment that are used at CERN. And these skills is going to be transferred back in the country to boost the economy as well. And then we also have ISOLDE that has been there for quite some time. And they have been very productive, and it's a long-standing pillar on the SA CERN as well. This is one of the very important pillars that we have. And it assists Itemba Labs in nuclear physics as well. And then we have theory. As I've said, you need theory so that they can explain what Prof. Ellis was speaking about to the politicians, to the general public, and to the young ones so that they are excited. And I will show towards the end that indeed this is what is happening. There are some achievements and impact of the program. Yeah. Over the past 15 years, we have been very productive in publishing articles in reputable journals. And this is also because of the collaborations with large international organizations like CERN, because there is rigor. There is expectations of high standards, and that comes back home in what we do to assist our researchers to also keep those high standards. And of course, it means also that our students are also trained from such systems that require rigor and quality work. And this is very unique, rather than just working alone as well. During the past 5 years, after the 10-year celebrations, we went through COVID-19. And some of our researchers, including their skills and the technology and the know-how, participated in assisting the government in fighting the pandemic. And this is really the impact of this consortium, that we don't only just focus on the science, but when the country says we are in crisis, we have to use our skills and our knowledge and put it into use. Students and emerging researchers acquire hands-on skills, as I've already mentioned, and in particular, technology transfer, in particular also contributing to the economy, but also some of them are immediately absorbed by this big industry in artificial intelligence, big industry requiring quantum computing. So we are having students that can almost be useful anyway, including in academia. Some of them have been absorbed in academia. But what is important, as I will show later, is our participation at CERN also brings the knowledge that uplifts our standard in terms of mathematics and physical sciences, which is a huge problem in our country. And therefore, I will show at the end that indeed, through DSTI, through this program, we end up actually assisting other governments of the other departments of the government. And this knowledge and technology transfer into local research institutions and industry is what we need. And it has been happening over the past 20 years. And in 2023, a new pillar, as I've already alluded to, on the technology transfer has been launched. And this is very much welcomed because it will assist us as a country as well. Yeah. And these are some of the students hands-on, not theory only. And this is very critical for our country as we need innovators and entrepreneurs as well. So some of the spin-offs is we push the boundary of computing by participating at CERN. Because in order to participate at CERN, you will need to have high bandwidth, and which means if we push for high bandwidth and connectivity, the country benefits. Yeah? These are the spin-offs of participating in programs such as these. And then, as I've mentioned, we need to do outreach. We need to also carry the future generation that should come and stand where we have trailblazed. And we participated in competition across the world, and some of our students actually make it to CERN through these competitions, and they do get beam time as well. We also have colleagues in the SA CERN participating in what we call the master classes, especially here at Itamba Labs, but throughout the country. As you can see, and these are very important to introduce particle physics at high school and primary level. Yeah. Not only do we participate in outreach in South Africa, but also continentally through the Biennial African School of Fundamental Physics and Applications, where most of the topics, astrophysics, particle physics as well, we do participate. And the pictures that you see on the right-hand side, this is the latest edition. That was 2022, which took place in Gqeberha at Nelson Mandela University, where the majority of the students from African continent came to get hands-on experience, as you can see on the bottom right, that really it's not coming to look at the slides and look at the mathematics, but you go in and have hands-on experience. And it's through our collaborations with CERN that CERN scientists could come and conduct this hands-on experience. Yeah? And the students are very excited because mostly the education has been theoretical. And when they start to really engage in experimental projects, they get excited. Not only our students, but we also engage local high school learners. Our scientists from CERN, they come and go out into schools to engage with a local primary and secondary schools, so, which is very important for us, because we believe that early interventions in primary and secondary schools are very important. And through the South Africa CERN program, in partnership with the South African Institute of Physics, we have been in every corner of this country, trying to bring those slides that John put there so that we communicate that science of Higgs boson to them in a language and sometimes in their languages, home languages. Because the group now, if you see in the room, is diverse enough to go across the country to start actually speaking about the Higgs bosons. And of course, sometimes, Honorable Minister, you will remember our country, we don't have state-of-the-art facilities, but that does not prohibit us to go and stand under the tree and preach the Higgs boson and its excitement and what it will bring to South Africa. We do that. Not only that, the teachers are very important, and there will be a session on outreach on teachers as well. Our educators are very important because they have to teach this Higgs boson to our kids. Otherwise, our kids are left behind. So we also train the teachers as well through the South Africa CERN in collaboration with the South African Institute of Physics, which is very important for us. And key to the program is diversity and inclusion. And throughout the year, we have programs on women in physics in South Africa, lunch seminars at institutions where they come together and discuss issues, scientific issues and challenging issues. And we make sure that they are indeed included in the South Africa CERN consortium, which is very important for us. And we do training internally, not only through CERN. As a program, we do training in particular targeting historical black universities or historical disadvantaged universities, so that slowly we can include them in our programs. And that is very important for us, so that when we train them, they can participate meaningfully in these international collaborations. And the impact, Honorable Minister, South Africa CERN assists the South African Institute of Physics to generate questions for the Olympiad. And we go to schools and conduct this Olympiad. And through this Olympiad, we identify talent. And in the top picture, it's a learner winning an Olympiad that was done for physics. And again, another learner from Hermanus, that's a learner from Limpopo. This is a learner in the bottom right, a learner from Hermanus. They were all identified through these interventions. And they could win our Olympiad. And through this program of identifying the talent, these students become the top learners in the country, successfully. So you can see the journey that the program has in nurturing, but not only just waiting for them to come, but start through with them. And as I was saying, it's an investment by the Department of Science, Technology and Innovation, but assisting now the Department of Basic Education to have best math and science students. So these programs are working. And just at the dawn of the switching on of LHC around 2007, that was before the formation of SA CERN, we were already embarking on outreach programs. And one of those outreach is the one that I embarked in the rural Mopani districts in Limpopo. And we were targeting 127 schools. And we were talking about the coming launch of the CERN when they switch it on. And at that time, we were excited. Newspaper articles were being published about us as CERN, UCT CERN in particular at that time. And I happened to have spoken about John Ellis about the Higgs boson. It was not discovered yet, but the kids were excited. And one of those kids was in grade 9, was Nkateko. She was amongst a pool, a sea of students in that ocean. And 10 years ago, we had the 10-year celebrations. I met her here. She was in grade 9 then, but for some reason she said, "You remember me?" I said, "No." She said, "You came and you were talking about this Higgs boson." And I was in grade 9, one of the learners. And she said, since then she went to do BSc in chemistry. But not only that, she said, then in 10 years ago, I'm currently registered with VETS MSc E-Science, and I'm working on search for new boson using machine learning techniques. Yeah? So we only not produce good science, we communicate this science, we also inspire the young generation. And as Nelson Mandela said, what counts in life is not the mere fact that we have lived. It is what difference we have made to the lives of others that will determine the significance of the lives we live. I leave you with that quote from Nelson Mandela. Thank you.
I think now I'm not going to summarize because he was speaking in English. But I'll call upon the DCO of NRF to assist me.
Just checking it's still morning. Morning, everyone. Really good to be here and representing the NRF. It gives me great honor to introduce the keynote speaker, the Deputy Minister, Nomalungelo Gina. And I think the key aspect here is when one looks at what one would want in a leader, particularly in the science sector, one really wants to look to someone who really understands the sector. And I'll read you through the Honourable Minister's CV, and I think you'll agree with me that we're very lucky to have an individual such as yourself, Honourable Minister, in terms of the fact that in terms of science, you want someone that understands the science, but you also want to understand the education aspect, which we've just heard about, getting to the learners. And most importantly, on the other end of the spectrum, we really want to understand about the innovation, technology, and transfer. The Deputy Minister of Science and Innovation of the 7th Administration was appointed in June 2024, and this is one of the key points. She's the former Deputy Minister of the Trade and Industry and Competition in the 6th Administration, so that comes with a whole bunch of skills that we really need within the science sector. The Minister started her political activism in the late 80s while at the Inanda Seminary School and as a member of COSAS. For the longest of time, her career was in education as a teacher. So I think she all understands that, whether you're a lecturer or a scientist, we're all teachers. And that was for more than 15 years. She was a member of SATU and ascended into leadership as the site steward for that area. And she represented KwaZulu-Natal, Northern Coast Regional Education Convener for several years. She was later elected as the KwaZulu-Natal Provincial Executive Committee of SATU and as its Deputy Chairman. During this time, she also served in the ANC Women's League, Regional Executive Committee for her region. She joined Parliament in 2009, where she served on the following parliamentary committees: Higher Education and Training Portfolio Committee, again, a huge link with her current substantive role. Whip for Basic Education. In 2014, she was the chairman for Basic Education and also chairperson for the Social Cluster, which again, in terms of translating science to society, is really, really important. She is the Provincial Executive Committee member of the ANC in KwaZulu-Natal, and she's also serving as the Provincial Deputy Chairperson of the South African Communist Party, SACP. She holds qualifications in education from the University of Zululand, public management from WITS, an honours degree from WITS, and a master's degree from the University of Venda, and is currently studying towards her PhD. So as you can see, we're very, very lucky to have the Deputy Minister here today, and we really look forward to, as the NRF, working with her over the next few years during the 7th Administration. Over to you.
Thank you. Thank you very much for the introductions. Okay. Let me thank you very much to our program director, who let me greet the Deputy CEO of the NRF, Dr. Peterson. Greetings to the chairperson of the NRF board in absentia, our Professor Musa Mashabela. When I see and hear the journey of the SA CERN, starting from the UCT CERN up to where we are today, looking at where our chairperson of the NRF board is and the position he holds at the UCT, you see a lot of interaction, collaboration, and the relation in this journey, and you say, indeed, we are supposed to be where we are today, and hopefully the dream of taking it in to other institutions, we are going to be realizing that. to the Managing Director of Itemba Labs, Dr. Victor Chivase, thank you very much. Professor John Ellis, greetings to you. There are so many knowns and unknowns that we are thinking about as we are seated here. And hopefully those puzzles, it's what the SASMs is going to try and find solutions to. Thank you very much for what you have shared with us today. Professor Azwindini Morongo from the University of Nelson Mandela, let me acknowledge you. Dr. Mike Landmont, again, let me acknowledge you. Sometimes it's difficult to start where I'm starting because I will end up leaving. In fact, I need to acknowledge each and every one of you in this room, but it's quite impossible. Let me say greetings to everyone who is here. Ladies and gentlemen, you are all important. I really greet you. It is really an honor that I am here representing the Department of Science, Technology and Innovation. The Minister, Dr. Blade Nzimande, wanted to be here. Unfortunately, before I go there, let me acknowledge my DDG. DDG Patel. Hey, without doing that, good people, if you don't acknowledge your DDG, you go back to that department, you call him. I'm not saying him specifically. Any DDG, any official, they will say, DM, when we go out there, you forget that you are there. No, I did not forget you, DDG, really. You know, we are family, so whenever we go out, I take you as if, it's as if I've spoken about you. All the officials from the department, really, I really greet you. Let me not be as if when I'm all out there, I do not acknowledge you, but there is my DDG that is here, that is leading here in this section, where DDG Patel, I really acknowledge you with the whole officials that comes from the department. I was saying, Minister, I nearly said to Minister Patel. But you'll understand, I come from DTIC. I was under Minister Patel. I just spoken about DDG Patel, you know. My minister, Leighton Zimande, wanted to be here, good people, but let me apologize on his behalf. He had to undergo another very important. He was taken by another very important engagement. Not to say this one is not important, but we share the work and the task in the ministry, in the department. So really, I'm here representing the ministry, representing the department. But he said, in whatever that happens, I must say, he's with us here. He strongly and passionately supports what is happening with SASM, and he will always continue on behalf of the department. We always sit together and say, with all the transformation agenda, with all the things that happens through this collaboration, really he's also part and supports what is happening here. I was saying then, as the department, we are here, and for us to be addressing on this very important occasion, we are excited. As you know, it has been said, we are celebrating the 15th year. Is the anniversary of this SASN, the 15th year of collaboration. Is there worthy a celebration for us as a country? Because it points at several important milestones that have arisen. We have witnessed that, seated down there looking at the journey that we have traversed for 15 years. Really, it has been heartwarming to say, as South Africa, we made that decision of making sure that we put ourselves in those big shoes to make sure that we are part of the globe when it comes to the science, the research that we have got in. When Professor Azundini was here, he expanded my vocab to say, we are here to thank the Majaka Mbiras. Mbiras. Thank you. In my language, I will say we are here to thank Izingalabuto, the trailblazers that we are here. Indeed, that was a good decision. Thank you very much. We are here to celebrate today. Again, we are saying the celebration, this 15th year celebration, it coincides with South Africa having assumed the most important chairship of the G20 in December. And as DTSI, we are mobilized to elevate science, technology and innovation agenda and strengthens partnership and collaborations internationally. And so the CERN collaborates as one of those tried and tested partnerships that we have. And throughout this year, we believe even through this collaboration, there's so much that we are going to be seeing going through as we celebrate a lot of collaborations that we're having as a country. We are in BRICS. We were in BRICS ministerial meetings in Russia last year, and we agreed as BRICS countries that a shared approach, including cost in R&D, will have to be undertaken on science, technology, and innovation. So there is convenience in the view that one country cannot do it alone if there is a need to succeed. So again, as we sit here to celebrate this collaboration, I think we all agree that as a country, we cannot succeed, so these collaborations are important. Again, as a country, when we look at the journey where we come from as the Department of Science, Technology and Innovation, we were pleased during the 7th administration to see President Cyril Ramaphosa taking a decision again that we need to de-link the STI from DHET. That was a good decision because the mandate that was given again was to say, let us give a very strategic focus to science, to technology and innovation as a country. Through this, the mandate that was given was that he wanted us to have a focus, a clear line of the side of what we all want to do as the STI to raise the level of the national system of innovation for the country. So all of us, as we are seated here, we are expected, and all of us, we are called upon to work very hard and to double our effort in making sure that when it comes to the issues of STI, we put South Africa on the map. This includes increasing the number of academics. This includes increasing the number of researchers and more PhDs in this area. This is what is expected of us, and that is a mandate that we have been given as a country for this 7th administration. South Africa's association with CERN is informed by, among others, our strategic objective of gaining access to critical and world-class global research infrastructure. We recognize global research infrastructure as critical for advancement of a number of our strategic scientific areas. These areas include research and development of innovation policies, boosting scientific knowledge generation, accelerating technology development, enhancing both technological and social innovation, and providing advanced scientific training for new generation and sciences and science managers. It is also our view that global research infrastructure also provides an enabling environment for established researchers to improve their performance, knowledge, and innovation outputs. The complexity, as well as a high developed construction and operation cost, teaches us that it is impossible for one country again or the region to build or operate these facilities on its own. Again, let me borrow from the words by Professor John Ellis, when a professor said, he talked about the facts that are known. That is the known fact, Prof, as to say, as the country, we cannot operate on our own. So we want to deep and we want to dive on that, as to say, that is what we have taken, and that's the decision how we have taken as a country, as to say, when it comes to building these facilities, when it comes to exposing our researchers, that is exactly what we need to do. Let us collaborate with other countries to expand the knowledge of our researchers. By this is why the collaboration between countries is often the most sensible route, and that is why we have taken that route. By collaborating, countries are able to address the research needs of worldwide scientific communities by using the best available knowledge, human capital, and resources in one specific scientific area with multi-source funding. Again, it is important that as countries we look at the issue of funding, of which it was touched in the presentations that have been made before me. As to say, it's one area that becomes quite critical, but we are thankful to the government again in South Africa, as to say, we are trying by all means, as to say, when it comes to the issue of funding, there is something that we are doing, and as we continue, we are trying to tap in so many other areas to say, how best can we make sure that we fund the needs of our R&D, we fund the needs of our scientists, because we really see that critical need that we need as a country when it comes to the issue of R&D, in building the economy, in making sure that when it comes to strengthening the economy of our country, this is the cornerstone and the backbone of that as a country. As the DSTI, it is also our belief that all research activities must contribute to globally benchmarked excellence in research outputs, human capacity building, research infrastructure development. As the department, this is consistent with our decadal plan. Informed by this thinking through CERN, South African researchers have been able to make mark in the global arena, contributed significantly to the major breakthroughs at CERN. We also benefited immensely from the opportunity to advance our objectives in the critical areas such as human capital development, high-performance computing, and need to the constantly strengthening our research and innovation capacity. I have no doubt that these efforts will inspire the new campaign we have initiated as the department to galvanize the interest in taking up STEM subjects from the foundation phase level and all the way to the institutions of higher learning. As Professor Azwindini was standing here, I was saying, indeed, Prof, it's one area where, as the department, we are really interested and we're investing in making sure that when it comes to building, allow me to use the word, the value chain, as to say, when you start from the initial stages, from the ECD level up to the levels of the institutions of higher learning, it is our mandate to say, how do we make sure that we arouse the interest of people to take up the STEM subject? How do we make sure, as the department, we demystify, we make sure that we break the chains, and we make sure that we make learners and the communities themselves to understand the importance of the STEM subject? How do we make sure that we make science being more understood by the communities and the learners themselves? How do we make sure that science becomes relevant? They understand the relevance of them taking up science subjects. How do we make sure that we make it attractive? So working closer with CERN, making sure with institutions of higher learning, working closer with people who are trailblazers, professors, people who are already there in the system, going down to the communities out there. We are really trying to make sure that we open up the minds of those learners as they take up, as we attract them to take up the science subject, even open up their thinking and the knowledge to say, when we talk to the issue of science subject, we are not only thinking about doctors, to be a nurse, to be a science educator as we used to grow up knowing, but what more is there for them? And I think really with the partnership as the department that we are having with our institutions, our entities, we are trying to break through that. And as a CERN, you are playing a vital role in doing that. And with our institutions of higher learning, we strongly believe that is what we are going to do, and we are going to make a breakthrough when it comes to that. We are excited through this collaboration program that several African scientists, we are able to start a career in South Africa, and others. You know, there are so many South Africans who have started a career through their involvement in CERN. And what is even more encouraging is that we see others who have qualified, and they are encouraged to say, after their qualification, they even come back to plow back in South Africa, and we see them coming back to do that after they have obtained their PhD degrees globally, overseas, and so forth. And that is encouraging. I cannot emphasize more the need of our scientists and the PhD graduates to return to the country after such enormous exposure and contribute to the development of the science in South Africa, including those who come back and teach in our institutions. That is very important. I'm pleased that there has been an increase in the participation by academics, researchers, technical staff, and postgraduate fellows from 15 to more than 60 since the beginning of this program. As an emerging economy and a third world country, this exponential increase of participation numbers, it is encouraging. The number of postgraduates that benefited from CERN program increased from less than 25 to more than 70 over the period of activity, and more are eager to join the program, which offers the first-rate international research opportunity. Again, that is very pleasing. As a result of our involvement in CERN, the levels of collaboration have matured to the establishment of the fifth group of this SA CERN, that is the Technological Transfer Group, as it has been mentioned. The establishment of the 5th group has also enabled the South African CERN Consortium to approach the Technology Innovation Agencies, that is TIA, within the Department of Science, Technology and Innovation, and the DTIC, and other government agencies for funding intended for stimulating technology transfer and incubation. And we are looking forward for our agency working together with the Department of Trade, Industry and Competition to make sure that that funding comes into being together with other government agencies to make sure that when it comes to the issues of incubation and the technological transfer, we don't find ourselves wanting when it comes to the issue of funding. And it's one thing that is at the level of government we are looking at, and I can promise that will be funding that will be available. In the world that is seeing great shift to digital economy through 4th industrial revolution, these collaborations are all meant to help us exploit the great potential of technology transferred to South African industry. South Africa, through the National System of Innovation, is pacing itself to grow faster in adopting new technologies from health, industrial production, finance, and other sectors of economy of international standards. The technology transfer that emanates from participating in the LHC research and innovation activities will also enable the SA CERN collaboration to expand its footprints into applied physics, engineering, and ICT. The SA CERN program has financed phase one of the technology innovation platform, that is CHIP, here at Itemba Labs, through the erection of a building and the purchase of equipment. And following phase one of CHIP, the technology transfer pillar will be implemented within the South African program as part of the broader CHIP strategy of Itemba Labs. We are looking forward to those programs because they are expanding and opening up more opportunities for other scientists to come and expand their knowledge here. Our department, over the past 15 years, supported researchers and students to participate in collaboration projects at CERN, which is one of the largest and most respected center for scientific research in the fields of nuclear and particle physics. I've been informed that this collaboration has helped to address the scarcity of supervisors or the supervisory skills in South Africa, as it makes use of the internationally competence to support the academic supervisor of graduate students. I'm delighted that in the recent years, the activities of the SA CERN program have focused on the integration of the historically disadvantaged students, as it was mentioned by Professor Mashabela, and via the associate membership. The growth of the participation was further facilitated by the development of the research infrastructure at our universities, such as the high throughput electronics laboratory that is seen to be existing at the University of Zululand. And I said, I know it has been mentioned that this is now existing at the University of Zululand, but I said, as an alumni of the University of Zululand, I need to mention that because that is one of the universities that is, we are said, when we talk of, we usually say previously disadvantaged universities, but sometimes when we put this word previously, it's as if it's now disadvantaged. We still have these universities that are still disadvantaged. Let us make sure that we try by all means to support such institutions. Really, I said, let me mention this and say how proud we are. And I'm happy that last year, I think I was coming from Brazil. We had a BRICS meeting in Brazil. At the airport, I saw a large number of students. When I engaged with them, it was a group of students from the University of Zululand. When I asked them, where are you from? They said, we've been here through Timber Labs. I was so excited. I said, indeed, when we talk to the issue of transformation, this is exactly what we're talking about. So that is what we are saying. And I can even declare here that in my calendar, in my schedule, I'm scheduled to be in the University of Zululand on Friday so that we can further discuss this as to say, when it comes to the issue of transformation, what is it that we can do to such institutions to make sure that we put them on the map when it comes to the support of such institutions? This is exactly what we want to do. So thanks again to the SASMs to make sure that we talk and touch on the previously disadvantaged institutions. Ladies and gentlemen, the South African economy has already benefited also from the exposure of students to big data techniques that are currently employed at companies such as Discovery, FNB, Shape Blue, Pivot Scientists, RMB, Discourse, AL, Standard Bank, Data Project, to name a few. Again, in the presentations before, there was a strong link to industry, the strong link of SA-CERN collaboration with strong industry. And we do see that we do have the database. We are happy to see that there is even the benefit that the industry is getting out of that. The partnership with CERN accelerated technology development, enhanced technological and social innovation, provided advanced scientific science managers. The inclusion of software and hardware engineering as key focus holds huge benefits for South African students as it facilitates participation by universities of technology. In the area of high-performance computing, a Tier 2 data node was established in South Africa that allowed the country to become part of the global network for hosting, managing CERN data. The Tier 2 node is located at the Center of High-Performance Computing, that is CHPC. I am encouraged by the focus in the capacity building program, which will help in developing skills on data transmission and management model for the MeerGuard SKA project. Going forward, we see CERN creating even more excellent opportunities to a new cohort of students, postdoctoral and research to work and perform research side by side with international collaborators at a scale and depth of technology transfer that is only realized once in 30 to 40 years. We also see CERN as an excellent breeding incubator for new talent, as it has around 88 countries collaborating, including BRICS states, Russia, China, India, Brazil, and South Africa. As a South African CERN collaboration continue to enjoy tremendous growth in student future academics, there will be an increasing need for students, postdoctoral researcher, and new faculty support. This support will cement SA-CERN's role as a leader of high-energy physics research on an African continent. The celebration of the 15-year milestone presents an opportunity to reflect on the past achievements, to imagine the future. There is a need to reflect on the impact of the SA-CERN program, both from the knowledge and the societal perspective, but also on the contribution and the advancement of transformation. Innovation excellence within the National System on Innovation. For me, the main thing that we need to ask ourselves is to say, how do we make sure that we communicate, again for me, how do we communicate the relevance of science to the community? How do we make sure that we are known for what we are doing? How do we make sure that whatever the qualifications that we get, they bring relevance, they bring solutions, they bring the answers to the questions that are troubling our communities out there? How do we make sure that the puzzles, we put together the puzzles that our communities are struggling with out there? For me, again, let us ask our questions. Let us ask these questions. Where to from here? When we look at the next 15 years, where do we want to see ourselves as the science community? How do we make sure that we open up for more other inspiring scientists to come in? But may I say this, may this partnership, may this collaboration through the SASM continues for the next 15 years and beyond, but can we open up more doors for more of those who are inspiring to come in? As the Department of Science, Technology and Innovation, we commit ourselves to this collaboration. We'll try to push all the barriers that are there. Yes, it might not be as easy as it is, but really the road has been traveled. We are committing that we are still going to travel. The next 15 years will be with you and beyond, and there's so many doors that will open for our young ones to come and solve the solutions that we are having for our country. Thank you very much, Program Director.
I think the best person to do the thank you to the minister will be the DCO.
Firstly, a big thank you, Deputy Minister. That was a great overview of what we really need to do as a country and what a special relationship we have with CERN. I think a key component is if we look at the key words below that CERN there is it's a celebration. It's a celebration of 15 years of excellence. In the NRF, we often talk about something called TIES, which is transformation, impact and innovation, excellence and sustainability. So when we look at a program that we've been so lucky to have invested in from the DSTI, we say, well, it's an outgoing program. Does it meet the TIES requirements? Does it meet the transformation aspect? So imperative in South Africa that the Minister was talking about the need to bring in historically disadvantaged institutions. And we can see a concerted effort there. We can see, and I had a long chat to my colleagues from University of Zululand, as well as the other universities. So the transformation aspect, the growing of students, the fact that we're going down to, as the DVC said, to the trees in the rural area, to find the rough diamonds, to make sure that we get them through, all the way through to PhDs and becoming leaders in their own fields in South Africa. So in terms of transformation, I think CERN is really doing something special. In terms of impact and innovation, if we look at CERN and we look at the impact it's having and the innovation it's having, the type of work we're doing, are we getting value for money? Wow, we're part of one of the biggest global experiments in the world. So a big thanks to the CERN leaders that are here. Thank you for involving us. Thank you for letting us be part of this really big global initiative. In terms of the impact of the work and in terms of the innovation, we can see we're moving very quickly in that row. Now, this is a very important component because remember, science doesn't come cheap, okay? And the minister's got to stand up there in Parliament and the Deputy Minister and face the parliamentary portfolio committees with other ministries also standing up there, whether it be health, education, defense, and they've got to argue for budgets. And I hate to say it, but money does count. And really, we need to make sure that we provide the ministers and the department with the type of knowledge that allows them to access the funds that we need, because we need more funds. Science is underfunded within South Africa, and we can just do so much more. Every time I see Imran, the DDG, as the minister said, you've always got to be on good terms with the DDG. Imran just looks at me and he says, Angus, you're going to ask for more money. Indeed we are. So we need to also help the DDG. We need to help the Deputy Minister. We need to help the Minister with that message as to why science is so important. I think we're really good at communicating the what we do. Okay, we need to be able to communicate the why. Not the why from the academic rigor point of view, but why we need to do it for society. What difference does it make to the average South African? Because the average South African is having a challenging time. It's a very difficult economy we have. We've got legacy issues, very deep legacy issues, and therefore we've got to make a really good argument as to why we want to invest in science and technology. Getting back to the E in ties, which is excellence, there's no question, if we look at CERN, the type of science they do, this is excellence par excellence. A bit of a pun, anyway. I never realized that Prof. Chavasa had so many jokes, but I'm learning today. So, no, really, if you look at the excellence and the type of work that that gets done at CERN, it's really, I mean, it really ticks that box, which ends up with the S, which is the sustainability aspect. Linking back to the financial sustainability of all of this, how do we increase our role in CERN? How do we translate it so that we can work with TIA, so that we can get the innovative stuff out there, so that we can go to the parliamentarians and we can discuss with them? Because when we speak to parliamentarians in South Africa nowadays, the key issues that we're talking about are transformation. We're talking about people issues. We're talking about daily issues. And we need to make sure that we can translate what we do here, which is absolutely pivotal and the foundational aspect. But it's an area we certainly need to improve on, is the way we communicate our key science to the general person on the street, because that's really why we're doing it. And the funny thing is, we have the best minds in the world, is we know that there is a direct line, but we need to learn to communicate it better so that people understand, and so that the minister can walk away and give us a call, and I can get a nice email from Imran Patel saying, yeah, we've secured the funding for this. So I'd just like to say, firstly, it is a celebration. From the NRS perspective, a big, big thanks to CERN and CERN leadership. A bigger thanks to the DSTI for funding all of this. To the CERN community, which are looking at here, a big thanks for all the hard work. All the committee leads, I know that they often get grilled quite a lot by their constituencies about where the funds go and how you manage them. But I'd just like to also thank you, Timber Labs leadership, for managing this program. I think it's a really important component to the chair of CERN. So a big thanks, and this certainly is a celebration. And I'd just like to give you all a round of applause, and then I think we've got a break. Thank you very much.
Thank you for being so kind and give me the opportunity to drive this vehicle so easily. Thank you, and I'll hand over to Gillian to make some announcements.
Right, thank you, Chair. Ladies and gents, that brings us to the end of our opening ceremony. I think we say thank you to all those who are online. We will close the live stream now. Lunch will be served from now up until 1 o'clock. because at 1 o'clock we reconvene in the same venue to continue with our program. So lunch will be served 2 places, in the foyer here and then also at the exhibition space. So if there's not enough space here, you're welcome. Some of our staff will direct you. For those of you who are participating in the program just after lunch, if you have your presentations on a thumb drive, if you could just liaise with the IT people at the back to make sure that that is set up. And then those of you who have poster presentations, remember it's e-posters, so if you could also just liaise with our IT people, Wendy I think in particular, and they will make sure that we upload that to the screen so that it's ready for this afternoon. I'm going to ask our dignitaries to just remain behind as people rush out so that we can take a beautiful picture with you before we take the DM on a little bit of a walkabout to blow her mind even further. Ladies and gents, thanks for being here. That's the end of session 1. And just a special word of thanks to Trudy and Beryl, our 2 sign language interpreters. Thank you very much.